Hi there. Welcome to lecture 19 of Machine Learning from Data. We are going to take a peek at unsupervised learning. And I want to emphasize it's just a peek. It's not in any way a fair treatment of this huge area. Okay. Now let's have a quick review of what we did last time. We talked about radial basis function. So that's another important, powerful, useful model. Okay. We talked about the non-parametric RBF for radial basis function, which basically extends the nearest neighbor by looking at all data points, weighting appropriately, and then summing up the contributions from each data point. So a weighted average of contributions from each data point. Further data points from the test point have less impact on the classification or prediction at the test point. Okay. Now, that's the non-parametric RBF. There's no training. It has pretty much all the benefits of the nearest neighbor algorithm and also the main computational drawbacks. Okay. So we ended up deriving the K RBF-network. So what were the steps? The first step was to view the radial basis function as placing bumps on each data point, and those bumps were now of a fixed height. Those are the parameters, the bump heights, and then each bump on each data point makes a contribution according to the height of that bump to the test point. Okay, and when we were done with all the math, we find that the hypothesis is a linear model, okay, with tunable features, where the tunable features come from being able to tune where we place the K bumps, the centers. Okay. And we talked about a simple method for picking those centers, which is this Lloyd's algorithm, pick the centers far apart from each other so they represent the data. And then we indeed do have a linear model with the centers picked according to the clusters in the data. So in principle, it's a nonlinear model in the centers, but we don't use the Y values in deciding where to put the centers, and so we're not really fitting the centers so much, more like just organizing the centers to represent the data. Okay. And I showed you what happens if we picked 4 centers and if we picked 10 centers, and you get the usual overfitting that's possible, and so you have to regularize, and that's what we see here on the right. Okay. Now, we've already seen unsupervised learning in 2 contexts. The first was to organize the data so that the branch and bound algorithm in nearest neighbor search for finding the nearest neighbor can be more efficient. Okay, so you store the data in clusters, and then when you go into a cluster and you come out with the closest in the cluster, you might be able to bound in such a way that you don't need to search the other clusters, and that requires tight clusters that are well separated. And then we just saw the use of sort of an unsupervised technique to find the centers, as far away data points to represent the data in the RBF network. Okay, so unsupervised learning is a useful preprocessor for organizing the data in supervised learning for specific techniques that we have already developed. And unsupervised learning is important on its own because, for example, you're trying to learn a language. So it helps to just listen to the language and build the patterns. Or it's helpful for Amazon to organize books into categories, even if you don't know exactly what each category means. Okay, and last time I showed you a peek at the kinds of information that you can extract just from unsupervised clustering. So on the left, we saw the multi-class version of the K nearest neighbor algorithm that classified the space, intensity symmetry into regions corresponding to each digit. And on the right, you just cluster the data. So you don't even have access to which data points are which digits. You just know intensity and symmetry for each data point. And now you do a 10 clustering, and look, the structure is very similar to the structure that you see with the supervised version, but in the supervised version, we know which digit is which. So all that remains after we've clustered the data is for someone to tell us which cluster belongs to which digit. And so you can see how clustering can help significantly with organizing the data before you get to the supervised learning task, so that you only need a few data points from each cluster to now have a fully, functional classifier, which would be a supervised classifier that, organizes the data based on lots of data, but then a few data points tell you what clusters belong to what classification. Okay, so we're going to start with clustering, and we're going to talk about it in a little more precise framework and develop some algorithm. It's a hard problem. It's an example of NP-hard problem. In machine learning, there are lots of NP-hard problems, but still we can build efficient heuristics for clustering. And then we will talk about probability density estimation, which is another very important task. It's an unsupervised task. Okay, and you can think of it as a generalization of clustering. So let's go to the board. I left the slide up so that you can have some context for the problem we're about to define, which is clustering. Okay, so clustering. Okay, and this is an example of unsupervised learning. Okay, And so in the unsupervised setting, you still have your data, but you don't have y values. So your data set is equal to x1, x2, up to xn. Okay. Now, you might have y values, but you can always choose to ignore them and do unsupervised clustering, just like we did for the RBF. We ignore the y values to get centers. Okay. So let's first define what it means to cluster the data. So you output a clustering of the data, a clustering of the data. Okay, and the first thing when you're outputting a clustering of the data is you need to know how many clusters. Now, there are some automated algorithms for deciding what's the right number of clusters, okay, but in general, that's an open research question. So for us, for our purposes, we're going to assume that the number of clusters is given. Let's call it K, and so we call this a K clustering of the data. Okay? And it's just the output of a clustering. So what's the task? The task is to just produce K subsets of the data. Okay. Produce K subsets of the data. Let's call them S1, S2, up to Sk. Okay, so you've produced K subsets of the data. And now I want to tell you what those subsets should satisfy. Okay, and so we're going to simplify the problem. Okay, so first, the subsets should be non-overlapping. So the subsets should be disjoint. Okay, so it's much easier to formulate the problem when you're looking for non-overlapping clusters. Now, you can easily argue that, well, does that make a lot of sense in practice? So, for example, if we're organizing books, so there's the bio books, and there are the math books, and then there are the overlapping books, the mathematical biology or the biostatistics. So, in many real-world applications, you know, there is an argument for overlapping clusters, or you could view it as there's the bio-only books, the math-only books, and the bio-math books. That's three separate categories. Okay, so you can, in some sense, get away with non-overlapping clusters by increasing the number of clusters, but that could lead to overfitting and so on and so forth. So, okay, you know, there are complications when you allow the clusters to overlap. So we're going to simplify and say that, you know, the clusters must be non-overlapping. Okay. And the second requirement is that the clusters should be complete. So they should cover the whole data set. So complete, i.e., cover the whole data set. Now you might argue again that, well, you know, what about outliers? Maybe we don't want to include outliers in clusters because they will just, you know, distort the clusters and maybe pull them in one direction or what have you. Yes. So there are all kinds of, you know, modifications and enhancements to the problem definition to make it, you know, closer to practice, but that'll make it a harder problem. So let's at least see if we can, you know, get anywhere with this easier problem. Okay. So what this means is that your subsets Si intersection Sj should be empty if I is not equal to j. Okay, so that means that they're disjoint. And the union from I equals 1 to k of Si should equal your data set D. Okay, so this is condition 1, this is condition 2. Okay, and so that's it. Output a set of clusters. And you look at me and say, well, that's trivial. I'll just, you know, partition the data randomly into k subset. Okay, so we need to make this problem a little bit less trivial by saying what more is required of the clustering. So what else is required? What else is required? Okay, and now we can go back, for example, when we talked about branch and bound, what made good clusters? And this is what typically makes good clusters. So the data points in a cluster, the data points, so two things, you know, make the clustering good. So what else is required? I.e., what makes the clustering good? Okay, so one, you know, from the branch and bound, we saw that we like clusters to be tight. So points within a cluster should be close to each other. Okay, that makes them tight. So enclosed. So for example, you can imagine that a cluster has a center, and you know, within a small distance of that center are all the points that belong to that cluster. then that would make all those points close to the center and therefore, close to each other by the triangle inequality. So points within a cluster should be close to each other, and points in different clusters should be far away from each other. Points in different clusters should be far from each other. Okay, so the within cluster spread should be small and the between cluster spread should be large. Okay, these are perfectly valid, criteria that we would desire. Okay, now we are going to mostly focus on the first criterion, okay, which is we would like to ensure the fact that, points within a cluster are close to each other, as close as possible. And we let the different clusters, the distances between different clusters take care of itself. Because in some sense, once points within a cluster are very close, then relative to that, the between cluster distance is going to be large. Okay? So what this means is that we're going to formulate a clustering error. So a way to measure, how good the clustering is. So we define a clustering error. Okay. And then the idea is to output clusters or output a clustering, i.e. output your K subsets so that you minimize the clustering error. And the clustering error is relatively easy to define. Okay. So what we will say is that, okay, so we can think of, simultaneously defining for each cluster a center. So define for each cluster a center. Now we could call it mu of Sj for cluster J, or we'll just call it mu J, okay, to indicate that it's the center for cluster J. Okay, so then we can define the error, the spread of cluster J, Ej. So this is the spread, think of it as the spread for cluster J, is just the sum of the squared distances to the center. Okay. So it's just the sum for all data points xi that are in Sj. Okay, so it's the sum, okay, over all data points that are in the cluster of the distance to the cluster's center, xi minus mu j squared. You can think of this as, how large is cluster J. Okay, and now we can add up the sizes of each of the clusters. So we take the sum from J equals 1 to K of Ej. Okay, and that's the sum of the sizes of all the clusters. And we can define this as an error measure. It measures how bad the clustering is. Okay, so we can take this as an error measure. Okay, and we will say that a clustering is good if this error measure is as small as possible, or a clustering is optimal if this error measure is as small as possible. Okay, you can think of this error measure as the sum over all data points. Okay, little n is equal to goes from 1 to big N of the distance between x sub n and the center corresponding to x sub n squared. Okay, so where I'm loosely using the notation mu of x sub n means the center for the subset to which x sub n belongs. Okay, so x sub n belongs to some subset, and that has a corresponding center. And so how far is x sub n from that center? Okay, this is called the k-means clustering error. The k-means clustering error. Okay, it's a famous clustering error. It's basically the squared, think of it as the squared sum of squared deviations from your center. Okay, and our goal is to find subsets and corresponding centers which minimize the k-means clustering error. Okay, now you will see that the center corresponding to xn is well defined. Okay, and why? Because every data point belongs to a cluster. So the clustering is complete. It covers the whole data set. point number one. Point number two, a data point cannot belong to more than one cluster. So it has only one cluster to which it belongs, and so a well-defined center, and that's because, you know, the subsets are disjoint, so no data point belongs to more than one cluster. So these two sort of requirements are in some sense instrumental in even just defining this error function, making it well-defined. So let me box this. Okay, I'll box it in red. Okay. So this is the k-means clustering error. Okay. So very simple. Okay. Very intuitive clustering error. And, you know, the task is simple, right? Output a clustering of the data, which is a collection of k subsets that are disjoint and cover the data. That minimizes the clustering error. Okay. So we could take the output. So the output of clustering is exactly the subsets S1, S2 up to Sk and the corresponding means mu1, mu2 up to mu k. Okay. Go minimize this, you know, nice simple error metric, you know, and output for me the subsets and the centers of those clusters. So the subsets are called the clusters, and the centers of the clusters, well, they're the cluster centers. Okay. Well, unfortunately, it turns out that this problem is very, very hard to solve computationally. Okay. And in a formal sense. So it's an NP-hard problem. Oh well. Okay. And we've seen NP-hard problems before. You know, the first NP-hard problem we saw was when we were talking about the linear model and classification. Can we find the linear model that minimizes the probability, that minimizes the number of in-sample mistakes? NP-hard. Okay. So machine learning is a source of many NP-hard problems, but we still need to do it. So we're going to build a heuristic, you know, which is an example of an alternating algorithm, which comes from a family of EM kind of algorithms, which we'll see later. Okay. That is very good at solving this problem. It produces good solutions. Of course, in the worst case, it can be far from optimal because the problem is NP-hard. Okay, but we need to do something. So let's develop the alternating algorithm, and that alternating algorithm is called Lloyd's algorithm. So Lloyd's algorithm. Okay. So there's no algorithm that can guarantee finding the optimal clustering that minimizes this error in polynomial time, or at least none that we know of. Okay. So Lloyd's algorithm is an example of what's called an alternating algorithm. Okay, because it alternates between doing one thing and then another. And it actually comes from a family of algorithms. So it's a special kind of alternating algorithm, which can be posed as an EM kind of algorithm. But we won't get into those details. Let me show you the algorithm. It's very intuitive. Okay? It says that, you know, we don't know how to solve this problem in general, but, okay, if you give me centers, mu1, mu2 up to mu j. Okay. Well, then I know how to solve this problem. So if you were to tell me what are the optimal centers, then I know how to solve the problem. Okay. Then I can solve the problem greedily. Okay. What does that mean? Well, if you've told me the centers, then there's a very simple prescription for identifying the subsets. For each center is going to correspond to a subset. And what am I going to do? I'm going to take each data point and assign it to the center that's closest. Okay. So you can think of the centers, okay, in two dimensions. If you give me the centers define Voronoi regions. Okay. You know, we've seen this before. Okay. So there's that guy, then there's that guy, that guy. So each center defines, in some sense, a Voronoi region. Okay. And now you look at the data points, okay, and you assign data points to the center that owns the Voronoi region to which that data point belongs. So if these are the centers in black, then the clusters are defined exactly by the points that lie in each Voronoi region. Okay? And it's easy to see that that's optimal because, you know, by definition, the distance from this data point to this center is closer than its distance to any of the other centers. So it's going to minimize that distance from the data point to its corresponding center. Okay, so each data point can be minimized greedily, and if you can do that greedily for each data point, that's optimal. Okay, very easy. Okay, the second observation is, if you give me subsets, if you give me subsets S1, S2 up to Sk, then I can construct the optimal centers. Then the optimal centers are easy to construct. Okay, and why is that? It turns out that that's related to the fact that we're looking at the squared errors. Okay, so now you've told me which data points are in each cluster. Okay, and because we're using the squared error, it's easy to construct the centers of the clusters. If we were not using the squared error, it might be much harder. Okay, and how? Well, it's an easy exercise for you to show that the center mu j, which minimizes, or thus the ej, which is the sum over x in Sj, so the sum of the data in my cluster Sj of the norm of x minus mu j squared. So this is the sum of squared deviations. The center which minimizes this is exactly the mean. So mu j star is equal to the sum from of all x in Sj of x, okay, divided by the size of Sj. So it's just the mean data point. And what's that? That's the mean data point in Sj. Okay, so that's interesting. If you told me what are the optimal centers, or if you gave me a set of centers and said you're restricted to use those centers, I can construct the optimal subsets. If you gave me the subsets and said I'm restricted to use those subsets, I can identify the optimal centers. Okay, and those two observations exactly together lead to this alternating algorithm. So let me show you the Lloyd's algorithm. So Lloyd's algorithm is very simple. Lloyd's algorithm. Okay. Step 1. Okay. Find centers. Centers mu1, mu2, mu3 up to mu k. How? Okay. So if it's the beginning of the algorithm, randomly. So either randomly for the beginning or as the mean vector in the respective cluster Sj. Okay. So that's the first step. Okay. So you randomly choose data points xn. Okay, so each center is a randomly chosen data point, okay, at the beginning. And as the algorithm progresses, you will construct the centers to be optimal for whatever the current clustering is. Okay, and once you have centers, assign data to centers greedily using the following algorithm. Data point xj gets assigned to the center, or let's call it x little n, gets assigned to the center which minimizes the distance to xn. Okay, so argmin over j. So find me the center that minimizes the distance to xn, and that's the center to which I assign xn. So you assign your data points to centers, okay, and always making sure that I assign the data point to the center that's closest. Okay? That gives me a clustering, a partition into subsets. Okay? Now that I have a partition into subsets, I go back, repeat until convergence. Okay. I go back and reassign and compute means, okay, according to the mean vector of the corresponding clusters. Then I reassign data points to centers. Then I recompute new centers as means, reassign, and so on. Now, how do I know that this is going to converge? The reason I know that this is going to converge is that in each step of the algorithm, okay, if anything changes, it is if anything changes, it is because either this in this step or this step. If anything changes, that means that this error function strictly improved. So let's see. Okay. If you have your clustering, okay, and you have your centers, and you decide to move a data point from one center to another, it's only because that center is closer. Okay. So that'll strictly decrease the error. And in this setting, if any of the centers are not the corresponding means, then by moving the center to the corresponding mean, you strictly decrease the error. Okay, so each of these steps strictly decreases the error. Okay, so every step here strictly decreases the error. So every time the clustering changes, the error strictly decreases. Okay, and the error cannot continuously strictly decrease forever because there are only a finite number of clusterings. So eventually you have to hit the bottom. Okay, so this algorithm is guaranteed to change, is guaranteed to converge after some finite number of iterations. But the problem is there are exponentially many clusterings, so it can take a very long time to converge, and it's not necessarily the case that it converges to the optimal. So there are many local minima in this, in this error function, and this can converge to a local minimum. But in practice, it works very well. Let's have a look at some examples. Okay, so let's see some examples. Let's see Lloyd's algorithm working on some data. Okay, so on the right is some data that we've seen before. Now a slight improvement in the initial step in Lloyd's algorithm, which picks centers randomly, is to pick centers that are well separated. So start with a random data point, pick as the first center, pick the next center as far away as possible, and then the next one as far away from those two, and so on. That gives us, these black centers. Okay, and the next step is to assign to each center the data points, the data that's closest to that center. That constructs, in this example, 5 clusters. Okay, and now you update the centers of those clusters, okay, to the mean data point within each cluster, and you can see this update, and you can keep doing this update over and over again, but it converges very quickly. It very quickly converges. Okay. Now, let me show you an application of this k-means clustering algorithm to the radial basis function network. Remember, the first step was to find centers, so we use Lloyd's algorithm to find centers. And look, okay, if we do 10 center radial basis function network, why 10? Well, I picked that because I know something about the digits data. There are 10 classes. And look at the beautiful, separator that we get. Okay. Now, if I pick a 300 center RBF network, then we clearly have overfitting. And so, if you're going to pick 300 centers, be ready to regularize. So, for example, you can use regression for classification, and then regularize the regression to get your final classifier. Or you should use something like cross validation to pick the number of centers.